Okay, let's get started with Module 9. Module 9 is covering human factors. At the very end, we're going to discuss hypoxia and spatial orientation.
Is human. For this reason, we've made mistakes as we conquered frontiers. And with skies beckoning, we tried and tried to fly, but physics wasn't on our side. Then with a little bit of hot air, we finally beat gravity and powered right into the wild blue yonder. And it wasn't long before we slipped into the First World War. Amazingly, more people were killed by poor decisions and sloppy training than machine guns and dogfights. But with lessons learned, we blitzed our way through into the Second World War. And aviation began to streamline. More power, more dials, more speed, but sadly, a lot more stress. So we introduced science, and the first rudimentary simulators started to trick reality. Then finally, the dust settled, and bombs were replaced by bums. And we soared passengers into the jet age. Pilots went from heroic risk-takers to wearing gold bars and wrangling with computers. And the airlines grew and grew. But so did the human factors, and they came thick and fast. And after several tragedies in the 70s, safety refocused on communication and teamwork. And in the 90s, we really started to look at the whole picture, not just at work and second jobs, but at home and in play. So now we recognize that human error can occur anywhere, anytime, in any system. So as we build our knowledge of human behavior, we'll continue to boldly go where we've never been before. Each facet of human factors is interwoven with the other. If an organization doesn't invest in safety, it's impossible for people to be safe.
Aviation is often held up as the paragon of new technology and the future already here. And yet, it's only people, it's only the human who can hold together this complex, shifting patchwork of technologies, of communication requirements, of pressures and goal conflicts. It's only the human who can do that. If we don't understand the human factor, we don't understand safety in aviation at all.
Good safety culture, supported by management, is the foundation, so people feel empowered and part of the bigger picture. Like all things, it's about enabling people so everyone contributes from the bottom up with good reporting, action and feedback.
I don't own safety. The chief pilot doesn't own safety. Anyone you see in our facilities must own safety. Otherwise, you'll never get a generative safety culture.
So in this series, we'll look at several aviation organisations across Australia. We'll get a direct insight into how they manage their safety and human factors.
Aviation is inherently a risky business. Inherently, we work in a high-risk environment. And part of that risk is putting young and enthusiastic people in expensive machines with passengers behind them.
I think it's really making sure that they feel respected within the group and they're part of the group, and that they can feel comfortable at any time asking questions and feel that they're not going to be persecuted or feel foolish because of it.
We spend a lot of time and a lot of money into our staff training, but it's a cost of doing business. It's a very important aspect of our business.
And to complete the picture, we'll be gathering the thoughts of industry experts.
We see aeroplanes crashing because very basic parameters like airspeed and attitude are not being monitored at critical phases of the flight.
Often that last link in the chain has actually become the asset and rescued that situation.
Really the big difference in aviation is the consequences of those errors.
Welcome to a deep dive into the high-flying world of safety behaviours, human factors for pilots.
I implore people to invest in researching and understanding human factors. It will help you not just in your piloting career, but also your personal and corporate life.
I did a quick Google search to learn about human factors experts. Then I kind of got lost in the rabbit hole. There are more human factors, degree programs, and specialized areas of human factors than I could have ever imagined. Many people spend a tremendous amount of time trying to prevent human error incidents. Keep in mind, aviation experts agree that over 80% of accidents are a result of human error. Included in that 80% are pilot errors, errors by maintenance personnel, even design flaws that should have not been missed, or human factor errors. As you will see, human factors exist in every single thing that we do, and as we all know, all of those things affect how well we do whatever it is that we do as aviation professionals. I was involved in the development of a surface detection piece of equipment. We had a group of 5 air traffic controllers working on this project. After several months, we thought that we had it close to perfected. We were at the point where we wanted to have the FAA's human factors professionals give us some feedback. In no time, they very nicely let us know that the piece of equipment was very nice, but it required too much effort from controllers to be useful. Too much interaction, too much interpretation, and even that the colors that we had chosen for the icons on the screen were all wrong. We were very frustrated, but in just about a week, working with the experts, we were able to address all of their concerns. In our rush to design and deploy equipment, human factors are sometimes not considered, and we usually end up regretting that oversight. In the National Transportation Safety Board's investigation, it was determined that a poor design of the handle that actuates the flaps and slats was the main cause of the incident. This is a human factors error linked to design. Secondary causes were the autopilot engaging and disengaging, and the one that we almost always see, pilot training.
This is the story of China Eastern Airlines Flight 583. They say that takeoffs and landings are the most dangerous phases of any flight. They're sort of right. A huge chunk of the videos I've made pertain to either takeoffs or landings. But that doesn't mean you're completely safe when you're cruising at 33,000 feet. The occupants of China Eastern Airlines Flight 583 found that out the hard way. On the 6th of April 1993, an MD-11 pierced the inky blackness of the skies above the Pacific Ocean at 1:10 a.m. local time. This was a flight between Shanghai and LA with 255 people on board. The plane had been flying for 5 hours and the cabin was still and quiet. The lights were dimmed and the passengers enjoyed a movie. On the flight deck, all was normal. The plane was at 33,000 feet. The plane was flying at 298 knots. All normal stuff. The pilots flying the plane right now had just taken over from the other crew just 20 minutes ago. The captain, who was the pilot flying, was seated on the right side today. Usually captains sit on the left. This was because the captain was instructing the first officer on some aspects. The flight had been uneventful for most of the flight, but now the plane started to encounter some light turbulence. The captain turned on the seatbelt sign just to be safe. The turbulence died down after a while. On the right-hand primary flight display, the captain saw what he expected to see. The primary flight display showed 0.82 Mach as the selected speed, but just under that, it showed 0.728 Mach in an open circle. This was the economy speed that the plane had calculated. It was supposed to be a bit higher than that, and so the captain tried to fix it. He tried engaging the speed mode and then disengaging it to see if that would fix the economy speed. No luck. Then he tried to correct the speed through the flight management computer. That did not work either. Suddenly, the plane started shaking, and they were enveloped by warnings. Their instruments told them that they were close to a stall. The stick shakers were active. The plane then began to pitch up. The autopilot struggled to level the plane, but something pushed the nose of the plane up. The plane was thrown into chaos. The plane was nosing up, and their speed was falling. Their plane was screaming at them, telling them that they were about to stall. Then the nose started to drop. The plane started to level out, but the nose kept dropping. Soon the plane was accelerating downwards. The autopilot now strained to pull the plane out of its dive. The autopilot was disconnected at this point, and the plane was pitching down by 5.6 degrees. Over the next 13 seconds, the plane continued this oscillatory motion 3 more times. It would go up, then down, rinse and repeat. By the 4th oscillation, the plane was pitched down by about 25 degrees at a speed of about 320 knots. The g-forces on the plane ranged between 2g and negative 1.2 g's. Throughout these oscillations, the plane kept losing altitude. By the time that they were at about 28,000 feet, the plane had lost about 5,000 feet of altitude. The plane's speed peaked at about 364 knots, but now the plane was under control. The oscillations were there, but they were much smaller. As the plane climbed back to 33,000 feet, the nose bobbed just a bit, oscillating between 5 and 8 degrees as it climbed. At 1:23 a.m., Flight 583 contacted Honolulu Aeronautical Radio Incorporated, or ARINC. They told the operator that they had a sick passenger on board. A few minutes later, they declared a full emergency as many passengers had been injured by, quote, severe turbulence. Oakland Air Route Traffic Control Center, or ARTCC, cleared them to make an emergency landing at Shemya. Once on the ground, the scale of the disaster was apparent. 2 passengers were fatally injured. 53 passengers had serious injuries, and 96 passengers sustained minor injuries. The U.S. Navy and the Coast Guard evacuated the injured passengers to hospitals in Anchorage. With the investigation underway, they got their first clue from the pilots themselves. When the whole upset began, the pilots had indications that the slats were being extended. But what are slats? Slats are surfaces that extend from the leading edge of the wing. Quite like flaps, they increase the surface area of the wing and allow the plane to generate more lift at low speeds. Low speeds, that's key here. If they were to deploy in flight, it would be chaotic. When the pilots saw this indication, they made sure that the slats were actually retracted. But what would need to happen for the slats to extend in flight? Well, not much. All that needed to happen was for the flap/slat handle to move just a bit. When the handle is in the up/retracted position, the slats are retracted. Now, if the handle moved just a bit to the 0/extended position, then that would deploy just the slats. Moving the handle further back brings out the flaps as well. But we still don't have an answer as to why the slats came out. The pilots thought that the turbulence might have caused it. But looking at the weather data and reports from other planes, they came to the conclusion that the weather was fine. The pilots mistook the vibrations from the slats extending at a high speed for turbulence. To see if the plane was sound, they took the plane into the skies to see if the slats worked as intended. Everything came back normal. This plane was working perfectly. They tried their best to simulate the flight environment. They struck the handle from the left and right to see if an accidental nudge would move the handle. They found that the handle might move if you hit it just right, especially in the right rear corner. This could happen if someone's cuff got caught on the handle. Moreover, they checked the plane out extensively on the ground, and the plane was fine. They then focused on the pilots. What were they doing at the start of the accident sequence? Remember the economy speed prediction thing that the pilots saw? The displayed value was less than what the pilot was expecting. At the start of the accident sequence, the pilot was trying to fix this issue. He was trying to fix this issue through the number 2 MCDU. This lower than optimal speed was probably shown due to an incorrect cost index. Before the plane takes off, you punch in a bunch of data, one of them being the cost index, and messing that up slightly can lead to errors like this. So the pilots are trying to re-enter the data, and the keypad that he used was very near the slat handle. So a slight nudge and the slat handle moved to the 0/extend detent. The slats came out. Slat extensions aren't instantaneous. The inner slats come out first, and then the outer slats come out. As they slowly extend, they change the aerodynamic properties of the plane. At first, the autopilot corrected for this change, but soon it was too great for the autopilot to handle. The autopilot is also why the pilots did not notice that the slats were coming out. It masked the effects of the slat extension for a while. Once the slats pitched the nose of the plane up, the pilots struggled to control the plane. The captain used more force than necessary to correct the problem due to the low stick force characteristics. This is not uncommon. The safety board was aware of 5 other incidents where an initial upset led to PIOs, or pilot-induced oscillations. This was because the pilots had not been given any training on high-altitude upsets and recoveries. In addition to all of this, according to an FAA mandate, the slat handle was kind of biased in the direction of extension, that is aft. The pulleys and springs were loaded in such a way that it was very easy to nudge the handle in the direction of extension. This was so that they could have slats in case of an emergency. In this situation, that bias acted against them. Something that could have saved the lives of the 2 people on board was the humble seatbelt. According to standard operating procedure, passengers were to keep their seatbelts fastened at all times, but since the flight was smooth, a lot of people did not fasten their seatbelts. So when the upset happened, a lot of people were thrown around and into the ceiling. What kind of a passenger are you? Do you keep your seatbelts fastened all the time or just some of the time? By the way, researching this video, I was reminded of a book I read a long time ago. It's called Airframe by Michael Crichton. The book describes an accident that is very, very similar to this flight. If that book is not based on this incident, I'd be shocked. Have you read that book? Do let me know if you feel the same way.
Using Powtoon.
Common human factor errors that have and will create unsafe situations. Let's go through them individually. Loss of situational awareness. Situational awareness is so important. This can include knowledge of where you are on the airport in relationship to runways and taxiways. Understanding what other traffic is around you and what is it doing. And your mental airplane. Crew resource management. Who is available that is able to help you fly the aircraft? This includes everyone, from the person sitting in a seat next to you, to the entire flight crew, to air traffic controllers, other pilots that may be on the radio, and even passengers. Lack of proper training. As an instructor, I intuitively believe that there is never enough training. There is never enough knowledge that we can obtain. Every tiny piece of information that we obtain is like an insurance policy for the future. We may never need a lot of that training, but if we ever do, we will wish that we had paid closer attention. Fatigue. Remember that self-check from the aeronautical decision-making? It's important. We'll spend more time discussing fatigue later in the module. The checklist. Why is the checklist so rigid? It could be done much faster if one person did the checklist while the other person completed other tasks, correct? Well, in the early 1900s, industrial engineers were trying to reduce human error in medicine. They developed the concept of using callbacks when communicating in the operating room. For example, the doctor says scalpel, and the nurse repeats scalpel and then hands the scalpel to the doctor. That is called the challenge response system. Speaking out loud reinforces what tool is needed and provides the doctor with the opportunity to correct themselves if that is not the correct tool. The same verbal protocol is used in aviation today, particularly with the checklist. There are many examples of aircraft accidents when a checklist either wasn't used or the pilots just went through the motions. Air traffic control. Yes, air traffic control makes mistakes. And yes, we make them frequently. Read back, hear back, and good aeronautical English will go a long way towards prevention of these errors. Human factors in maintenance. Maintenance professionals are just as susceptible to fatigue, misreading a document, or cutting corners as the rest of us. Human factors are a large part of aircraft maintenance. Design and aviation. This area of aviation requires significant attention. Aircraft have crashed because of a part that went one place could also be installed on the wrong place. Aircraft designers are now designing port and starboard parts so that they can't possibly be misinstalled. Automation is everywhere. We all have to work hard to keep up with it. Like I said earlier, train, train, and when you think you have trained enough, train some more.